So here is the issue. I am horrible at streaming. I've genuinely got no clue how to do things. Yeah, okay, at least you can hear things. Actually, it's still kind of quiet. I'm gonna make it a bit louder, like this. Hey, 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 check, 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 check. Ah, fuck it. So here is. Oh, wait, no. So here is the point. I don't have patience, time, or skills to to make a clock overlay. I was checking, like, honestly, I think it might be easier for me to code it than to find an existing solution because I'm illiterate with Google but okay at coding, which is like a fun combination, to be completely honest. Um, yes. So I have this wild concept. This is like me just attempting it, but ambitious perhaps. So there is a list of so-called millennium math problems, which is like math problems that A are not expected to be solved anytime soon, B are like extremely relevant to the field of mathematics or just any field, and they're sort of detrimental problems that were chosen by this place, the Clay Mathematics Institute, for the new millennium, for the third millennium of sort of humanity. Well, I know it's not third millennium of humanity; it's just the Jesus Christ millennium, I guess. But anyway, so my idea was obviously I'm not gonna solve it, to be honest. However, has any relatively normal person who is not a very hardcore mathematician ever tried? No. Should I do it? Probably not. Is it gonna yield anything at all? Probably not. Am I gonna at least know a lot about one of the problems and be able to do something about it? Do know? No, yes. Oh, hi Gabby. Yeah, I took really long to start the stream because again, I may know how to code. I don't know how to set up a stopwatch for the stream, so there is none. And this is gonna be part one of me researching this thing. I'm gonna save the VODs and try to later make it a YouTube video. And I will use the duration of this one as the time. And once I manage to get a stopwatch, like a clock here, I will start it from the number of hours I spent on this stream. I wanna count total number of hours I spent on this topic. Like essentially, I'm curious what happens if an average-ish person who is not a mathematician spends, let's say, 100 hours trying to research a millennium problem. Yeah. So I'm gonna look a little bit at the history. So in order to celebrate mathematics in the new millennium, the Clay Mathematics Institute of Cambridge, Massachusetts, CMI, established 7 prize problems. The prizes were conceived to record some of the most difficult problems with which mathematicians were grappling at the turn of the second millennium, to elevate in the consciousness of the general public the fact that in mathematics the frontier is still open and abounds in important unsolved problems, to emphasize the importance of working towards solution of the deepest and most difficult problems, and to recognize achievements in mathematics of historical magnitude. The prizes were announced at a meeting in Paris held on May 24th, 2000 in the Collège de France. 3 lectures were presented. Timothy Gower spoke on the importance of mathematics. I'm not even going to watch that. The 7 Millennium Prize problems were chosen by the founding scientist advisory board of CMI, which conferred with leading experts worldwide. The focus of the board was on important classic questions that have resisted solutions for many years. Following the decision of the Scientific Advisory Board, the board director of CMI designated 7 million prize fund for the solution to these problems, with 1 million allocated per problem. It is of note that one of the 7 millennium problems, the Riemann hypothesis, formulated in 1859, also appears in the list of 23 problems discussed and addressed in the address given in Paris by David Hilbert on August 9th, 1900. So the rules are simple. If you solve it, you get $1 million. Not that I think I can solve it, but I really want to see how far you can get. The problems include Birch and Swinnerton-Dier conjecture. Don't even know what it is. Relates the number of points on an elliptic curve mod P to the rank of the group of rational points. Beautiful. Absolutely, I have no clue what this means. The Hodge conjecture, the answer to this conjecture determines how much of the topology of the solution set of a system of algebraic equations can be defined in terms of a further algebraic equation. Again, topology, know nothing about it. P and P. Yes, so this one I've heard about. Is it basically it states that if you can check that solution to a problem is correct easily, that means that the solution to the problem has to be easy as well. This is the point. And yeah, the PNP stands here. Yeah, the typical NP problems, that Hamiltonian path problem, which is the sort of energy path problem. Given n cities to visit, how can one do this without visiting a city twice? If you give me a solution, I can easily check that is correct, but I cannot so easily find a solution. Cool. Riemann hypothesis, the most famous one. Actually, maybe not the most famous. Maybe the most famous is Poincare conjecture. The prime numbers theorem determines the average distribution of primes. Essentially, prime number distribution. Young-Mills and mass gap. Experiments in computer simulation suggest the existence of a mass gap in the solution of the quantum version of the Young-Mills equation, but no proof has been found. Poincare conjecture is from French mathematician Henri Poincare. If the three-dimensional sphere is characterized as the unique, simply connected three-manifold, well, okay, I've heard about it, but I don't understand even what's going on. Beautiful. Now, what I'm doing here. So this is the one that is of interest to me, because truly and deeply, I study aerospace engineering. I've learned about the Navier-Stokes equations. Why is that a millennium problem? I don't know. They do seem complex, but they just seem like sort of, constrained 3D, three variable partial differential equations, which sounds difficult, but not that difficult. So I want to know what's it all about, and that's the single one that I will focus. So this is the equation that governs the flow of fluids, such as water and air. However, there is no proof for the most basic equation. One can ask, do solutions exist and are they unique? Why ask for a proof? Because a proof gives not only certitude, but also understanding. Essentially, we don't know if the problem can always be solved, which means that we have to use funky, fancy supercomputers when we want to compute fluid stuff. Turbulence is entirely not predictable at the current state of science. And yeah, I want to know what's it all about. How much can an average aerospace engineer with little experience do about it? No clue. So Navier-Stokes equation which governs the flow of fluids. Yes. Actually, I didn't know that this is how he looked like. His hair looks like turbulence. Okay. Actually, I'm curious to read the rules. Rules were adopted by the board. Please. Solution particular, please note that CMA does not accept direct submission of pro solutions. Statement of the rules procedure, CMA will not offer any further guidance or advice. All three of the following conditions must be satisfied. Proposed solution must be published in a qualifying outlet. at least 2 years must have passed since publication, and the proposed solution must have received general acceptance in the global mathematical community. Essentially, they want to prevent themselves from being spammed with wrong solutions. Okay, cool. This is not clickable. Fun. Oh my god. What a statement. Waves follow our boats as we meander across the lake, and turbulent air currents flow our flight in a modern jet. Mathematicians and physicians believe that an explanation for and the prediction of both the breeze and the turbulence can be found through understanding of solution of the Navier-Stokes equations. Although these equations were written down in the 19th century, our understanding of them remains minimal. The challenge is to make substantial progress towards a mathematical theory which will unlock the secrets hidden behind them. I am so curious to understand what the issue is. Like, it obviously doesn't seem like an easy problem, but like I don't get it. I don't know. Why is I love how further resources is not really like a thing. Okay, advances. The fuck? Uh-huh. I knew this problem would arise where like it's hard to find the problem to be defined. Okay. This is better. I have an untitled document, which I'm gonna call, how do you spell Navier-Stokes equation? Good question. Beautiful. So, existence and smoothness of the Navier-Stokes equation. So essentially prove that there is always a solution and that it is a continuous one, or smooth, I guess. Don't even know the difference. Good for me, I guess. I want to see where this leads. Charles L. Pfefferman. Princeton, Austin. Navier-Stokes existence and smoothness at Austin. Lecture. The wide audience, historical background of this problem, why they have resisted many years. Oh, that's nice. So I can actually watch it. That might be useful. Let's watch it and see what the problem is.
Oh, welcome to the 5th of the 7 lectures on the clay millennium problems. I'm glad to see that this beautiful spring weather has not won out against the attractions of these talks. It's probably unnecessary to explain again, but that these problems are unsolved. The lectures are intended to give you an idea of the nature of a few of the especially important unsolved problems in mathematics, what they're about. They are not reports on the solutions of the problems, as someone seemed to think last time. The solutions will require new ideas, new approaches. And
what I'm trying.
I think I said before, the first lecture, to get $1 million, this is probably one of the most difficult ways to get $1 million.
Yeah, to be fair, this is like probably substantially harder than winning a Nobel Prize, generally speaking, because you can just do like an advance in something. You have to solve a specific problem. So again, my expectations are extremely low, but even if I just get to understand the problem properly, they'll make me happy.
Dollars to solve one of these problems. Anyway, our speaker tonight is Louis Caffarelli. He was born in Buenos Aires, is of Italian descent with a dash of Greek thrown in. He did his undergraduate and graduate work at the University of Buenos Aires. But after his PhD, he went to the University of Minnesota as a postdoc. And 6 years later, he was a full professor there. It was at Minnesota that he began working in partial differential equations, which is became his main mathematical love and the area of most of his research. He also fell in love with and married a student in Minnesota, also from Argentina, Irene Gamba. She is now a professor here at UT in mathematics. After his Minnesota years and before coming here, Caffarelli spent time as professor at the Courant Institute at NYU, the University of Chicago, and the Institute for Advanced Study. Since 1997, he's been a professor and Sid Richardson Regents shareholder here at UT. If I list all his honors, we'll never get to the lecture. He's a member of the U.S. National Academy of Science and a foreign member of several other countries. His work has earned him several prizes and medals, including the Bochet Prize of the American Mathematical Society. He has an honorary doctorate from the University of Madrid. He's author or co-author of over 160 research papers. In his spare time, he likes to play piano and is a serious chef. During his Chicago years, I'm told it was said that the best restaurant in the city was Chez Caffarelli. But to get on toward the lecture, one of those 160-odd papers was written 20 years ago by Caffarelli, Cohn, and Nierenberg. Here's the review of it. Its title is Partial Regularity of Suitable Weak Solutions of the Navier-Stokes Equations. And I understand that that's of course a progress toward a solution of tonight's problem. And I'm told that in the last 20 years, in spite of the importance of the problem, there has been essentially no more progress. But let's let Professor Caffarelli tell us about the problem.
Okay. The problem with beautiful introductions is then you talk and mess it up. So, but okay, well, it's a pleasure to be here tonight. So let me start by writing what the Navier-Stokes equation is. It's a simple mathematical model to describe the way an incompressible viscous fluid flows. And yeah.
Love the quality of
Okay.
2000s recordings.
So what I thought tonight, what I'm going to do is I want to first give you an idea of what does it mean, a mathematical model of a physical phenomena. Then describe a little bit what each term in the Navier-Stokes equation means.
I mean, I actually studied this in my aerodynamics course at uni. I think the thing is, again, the equation was really easy. Like, I think, okay, well, it's not easy, but I think I can derive it because it's just conservation of energy, conservation of mass, and conservation of momentum written in differential form and united by a continuity condition. Basically, like continuity meaning like if an atom of fluid moves, it moves. Like it can't just like suddenly create anything nowhere. Like it has to be continuous. Like that was sort of what I got from it. I'm able to derive it, I think, if I'm given enough time. I want to hear what's difficult.
And finally, sort of discuss what are the difficulties of the problem. Okay, so the matter of modeling the surrounding world is something that comes from the beginning of mankind. I think the movement of the planets, the trajectory of a projectile, the hydrology, rivers and bridges and so on. People have been trying to sort of understand and predict the dynamics of the world around them. And through the years, they slowly develop a series of laws and methods. I was recently seeing once more the Leonardo Codex, that Lexington Codex that 5 or 6 years ago was bought by Bill Gates, and that the American Museum of Natural History had a beautiful presentation in New York when we were there. And there, Leonardo studies the flow of water and basically sort of says the principal relations, what is viscosity, what is pressure, what is capillarity. So the ideas have been there for many years, but it was not until the development of Newtonian mechanics that those concepts that people were able to write those concepts into mathematical formulation, into mathematical modeling. So the Navier-Stokes equation was precisely written by Navier and Stokes. Here is a picture of Navier. Here, this is Stokes. It really was written by Navier. Navier was a French hydrologist. I think the sort of the Napoleonic schools had a big influence in the development of fluid dynamics and many continuum mechanics in general. Navier was hydrology was well known at his time for the design of bridges and channels and so on, and was just sort of a little bit of a side work for him to write the Navier-Stokes equation, and he wrote it in very heuristic grounds, but wrote the correct equations. And so about 50 years later, Stokes wrote it in the context of a full theory of fluid dynamics. So let me discuss a little bit what is the nature of a mathematical model. So most of you know many simple mathematical models. Probably the simple ones is the fact that if you throw a stone, the trajectory of the stone is, at first approximation, a parabola. And therefore, you may predict the trajectory if you know the initial position and velocity. In other words, this sort of model you attain by reconstructing velocity and position, right, out of the simple law that acceleration due to gravity is constant downwards. And then from there, you write you can reconstruct the position. Of course, this is a very simple model, and if you want to write a more accurate one, then you have to take into consideration wind speed, the shape of the rock, the initial spin that you give to the rock, and so on. So in reality, given a physical phenomenon, there is a full family of models or different sets of equations that we can write to describe the same phenomena at different levels of complexity. For instance, in baseball, right, the parabola model is probably reasonably good for the outfielder that throws the ball far away to send it back to the pitcher. So it basically points up, throws the ball, and the ball makes a parabola, and the pitcher receives it. But if you want to reproduce a sophisticated pitch, then that's no parabola, right? That has a lot of spin, the wind enters into consideration, and so on. But such a mathematical model, independently of how accurate reflects reality, it has to have some internal consistency. For instance, again, in the parabola model, you can prescribe the initial position and initial velocity with which the outfielder throws the ball, or instead you can, prescribing initial velocity, you can prescribe 2 points, the initial position and the points where you want the parabola to go through, which is really what the outfielder does. I mean, he sort of solves the inverse problem in his mind and throws the ball in the right direction, but he's solving the problem of where he wants the parabola to go. And this is another acceptable mathematical model. But if you try to prescribe velocity and the point where the trajectory goes through, most of the time you are overdetermining the problem and you won't be able to solve it. Okay? Or if initially, instead of giving the full velocity vector, you just give the speed, the ball can go in any direction. Nobody knows where it will go. So the problem in that case is undetermined. So there is this minimum self-consistent requirement for a model, which is to be able to sort of within some reasonable set of data to find unique solutions to the equation. Okay? In other words, you want to say, if you give me this data, then I can tell you that the problem will evolve this way. Okay? That makes, so this is self-consistent. It has nothing to do, well, it has something to do with the heuristic of reality, but it has nothing to do with the model really representing an aspect or another of realities. So minimum requirement of any mathematical model. On top of that, you can also require some other reasonable common sense properties. For instance, if you have a problem where energy you expect it to dissipate, that indeed what you call the energy will decay, that velocity and acceleration will not become infinity, because that doesn't make too much sense physically, and so on.
Consistency.
Okay? So, as we will see, the Clay foundation problem about Navier-Stokes equation is concerned precisely with this issue of self-consistency, that is, existence of acceptable solutions and velocity remaining finite, and not with the accuracy of the model to reproduce reality. That's sort of not a mathematical problem, that's a scientific problem, but of a different nature. The mathematical problem is this internal consistency problem. Okay. So, so what is the physical phenomena that Navier-Stokes equation represents? Well, when I was thinking how to explain, I tried different type of models, and I was not satisfied with anyone. And finally, I thought that the correct version of the model was the gourmet one. And the gourmet one consists of the following. You take a bottle of olive oil with no air inside, so full. You put a little bit of oregano and red pepper as tracers. You shake the bottle really well, and then you sit it on the table. And the fluid is moving. And so what you want to do is you want to be able to reproduce how that fluid with that initial velocity will evolve into rest. Okay? So let me point out that this sort of experiment has many similarities with the throwing of the rock. Okay? In some sense, the initial shaking of the bottle corresponds to the swinging of the arm, where you are sort of giving the fluid some initial velocity. Okay? And the releasing of the stone corresponds to putting the bottle on top of a table and then let the thing evolve according to its own internal workings, its pressure, its friction, and so on. Okay? And also, both models have mathematical similarities, and these are the ones I want to stress. First, both models are the simplest most economic way on describing the phenomenon under consideration. So Navier-Stokes equation is the simplest family of equations that you can in some sense, create to try to describe a viscous flow. Also, both are reasonable under reasonable conditions. In other words, if the velocity increases too much, if you are looking at a model where the oil is engine oil and starts to burn and reaches very high temperatures and so on, then the model is not that good anymore. But what is more interesting, and I think I want really to stress, because I think this was the great achievement of the mechanicists of the last century, is that the idea in both, in the parabola model, what you take is sort of rates of change, right? Discrete rates of change, velocity at time 2 minus velocity at time 1, and then you take smaller and smaller and smaller rate of change and transform the average problem into an instantaneous, into a infinitesimal equation, right, which is acceleration equal to minus constant downwards, okay? And here too, the great achievement of these people was to study these bulk quantities, these bulk average laws, reduce it to smaller and smaller physical domains and intervals of time, and that will allow them to transform these bulk laws in infinitesimal equations. And this is one of the threads I want to follow, okay? And both mainly, those equations, what they do is simply balance the acceleration with the forces, internal forces in the fluid. Or faster than any given particle, then the flow pulls that particle faster. And I'll try to later explain that idea a little bit more in detail. Okay? So before doing that, I want to take some time. So what I plan to do is I plan to discuss what each of the 4 terms here are: incompressibility, well, acceleration, more or less everybody knows, pressure, and the viscosity effect. But before doing that, I want to take some time, because I think it's important to understand why Navier-Stokes equation is difficult. I want to take some time in discussing the 2 ways which usually people in continuum.
Yeah, probably working on the speed. If anyone comes in, they're gonna be fucking not having fun in this stream, but my bad, that's the way I like it.
Mechanics records data. Okay? There are 2 different ways, and these are Lagrangian and Eulerian coordinates. Okay? And that's why I chose the oil with the oregano and the pepper, because it's, I think, really probably the best way to explain it. Okay? So Lagrangian coordinates, you have the bottle, the fluid is moving, and you gather information from each individual particle moving on the flow. Okay? You have a particle of oregano, pepper, maybe a little drop of oil, and it's like if you were able to put in each little drop a set of sensors, right, and then receive the information that the particle is moving, the oregano is moving at such a speed, with such acceleration, with such density, and so on. Okay? So for instance, the data table in Lagrangian coordinates will be the following. I'll label the following particles, and then after 1 second, 2 seconds, 3 seconds, I say what the speed, or what is the acceleration, or what is whatever that particle is doing. Okay? In Eulerian coordinates, instead, what you do is you concentrate in every physical point inside the bottle. So you concentrate on each particle and register what is going through it. If oregano goes by, and you never see it again. You keep looking at that point, and you just concentrate what happens there, and you record what the data is doing there. Another way of thinking on it is, suppose you have a crowded highway, right? And Lagrangian coordinates would be if each car is reporting to you, is giving information to you. While Eulerian coordinates...
Yeah, it's pretty common in fluid mechanics to essentially focus on a cut and the flow through a cut, or like a buoyant. Because that's the easier way to depict flow, because there's, well, infinite number of particles, right? Like each molecule is technically its individual object, but it's so heavily correlated and has so many intermolecular forces. So it's kind of like odd to look at it from each molecule perspective, without quantum computers at least. So it's easier to see at the change through a volume or through area.
Is like a helicopter hovering over the highway and just looking what happens at this point and at this point. And the helicopter doesn't follow each particular car. Cars go by, right? He just records what is the speed of the car going through this point at this time. Okay? So, for instance, this would be the velocity field in Eulerian coordinates at a given time t0. You're looking at the space, and here you have this velocity, and so on. Okay? So in Eulerian coordinates, you only see a particle as it goes through a point. You never see it back. And so basically, what the main quantity you record in Lagrangian coordinates is the position at time t of the particle that you label with some name at time 0. Okay, so your name is x, and you say that particle at time 0 I call x, right? I call whatever, now is in position y. So Lagrangian coordinates, the main description of Lagrangian coordinates is by giving the position of every particle at every instant of time. Okay? While for the Eulerian observer, since he doesn't care about particles, the central information he has is just the velocity field that is going through any fixed point in space. Okay? So yeah. Why do I take this, the time to make this discussion, we'll see later, is because in fluid mechanics, both concepts in some sense mix. Okay, so let's keep this for a minute in the refrigerator. We will discuss it later. Let me now start to discuss the terms and the considerations. So the first statement in Navier-Stokes equation is that the fluid is incompressible. Okay, so we are all basically
density fixed.
So we all basically have an heuristic idea of what compressibility means. It means to just take in some substance or material and by pressing it, reduce its volume. Right? Gases are usually compressible. You have a bottle, you squeeze them, they can reduce the volume. Fluids are usually, under reasonable physical situations, uncompressible. There is no way you can reduce its volume. Okay? So this is the first statement of the equation. Now, what does it mean mathematically? Okay? So you can say what it means mathematically in Lagrangian coordinates or in Eulerian coordinates. In Lagrangian coordinates, it means that any little parcel of liquid or fluid you take, if you follow it through its life, it's going around and around and around and make the form, so maybe very long, very stretched, and so on. Nevertheless, the volume is always the same. That's what incompressible means. Okay? Lagrange, in Eulerian coordinates, you cannot talk about the volume traveling around. You have to fix your attention in a piece of space. So in Eulerian coordinates, you just take any fixed region and you look at the flow entering and going out instantaneously in that region. You say, okay, here there is flow coming out, on the other side there is flow going in, I average it all, whatever is in and whatever is out, I add it up, I have to get 0. Incompressible in fixed space means that whatever goes in has to go out somewhere else. Okay? Now, here I want to stress then this beautiful idea of continuum mechanics. This is something that I can apply to any little volume of space. I can apply to this area, to this area, to this area, to this tiny area. And it's additive, it superposes this property.
Yeah.
Therefore, I should be able to express that by an infinitesimal relation. Okay? And the infinitesimal equation, I just put it here for you to see, in Lagrangian coordinates, simply says that the determinant of the differential of y with respect to x is 1, and in Eulerian coordinates that the divergence of the velocity field is 0. And it doesn't matter what it means, but what is important is this idea that you can, by applying the bulk property to smaller and smaller and smaller domains, rewrite that as a differential equation, as an infinitesimal relation.
Yeah.
Okay? So much for incompressibility. I'll discuss a little bit later what is the meaning of that in terms of Navier-Stokes equation, but that's what incompressibility means. So acceleration, well, I think more or less all of us have an idea of what acceleration is. Or if you speed on the highway, it's linear acceleration. You take a turn, you have centripetal acceleration. So basically acceleration is just the instantaneous rate of change in the velocity of any given particle in the flow. You take a particle, measure its velocity at some time, measure its velocity a little bit later, make the infinitesimal quotient, take the limit. That is acceleration. Okay? Now, I want to stress a very important point about acceleration. That is that acceleration is a Lagrangian concept. In other words, to compute acceleration, you take a particle at a time, you look at it a little bit later, and see what is the instantaneous rate of change. Okay?
Yeah.
In Eulerian coordinates, to compute Eulerian coordinates instead, the situation becomes much more problematic. And the reason is that the velocity field, when you try to compute acceleration in Eulerian coordinates, appears twice. Okay? Appears first because velocity is changing, but also appears because the formula for acceleration says that you have to compute the velocity of whoever is going through point x at time t0, but also you need to know the velocity of that same particle an instant afterwards. That's what is going through point x at time t0, but also you need to know the velocity of that same particle an instant afterwards. That's what acceleration says. It says look at the velocity of the particle now, look at the velocity a little bit later of the same particle, and see the instantaneous rate of change. But the fluid has taken that particle away from x. In Eulerian coordinates, you are looking at x, and the particle is not there anymore. The particle has drifted away due to the velocity field itself.
That's fair.
So the particle is here, and an instant of time later, the particle has drifted away. And that means that when you try to write the formula for acceleration, the velocity appears in a non-linear fashion. Okay, when you do the increment, you have to consider the velocity not at x, but at the point where the particle has drifted by the velocity field itself. And that means that acceleration, which is so beautiful and simple quantity in Lagrangian coordinates, it becomes a non-linear quantity, complex non-linear quantity in Eulerian coordinates. Okay? And I think this is basically the course of fluid dynamics. The course of fluid dynamics is that you constantly match quantities which are natural in Lagrangian coordinates, like acceleration, with quantities like stress, which are sort of natural concepts in Eulerian coordinates, which are you match dynamic concepts with the static concepts and so on. Okay? And that's why equations in fluid dynamics are so difficult, because you write them in a way there is a piece that doesn't match. You write it the other part doesn't match. Okay? So let me go a little bit to the right-hand side. Okay? So the right-hand side says acceleration on the left says is due to the pressure gradient and the viscous effect. So let me discuss a little bit about pressure. Okay? I think that sort of, at least mathematically, pressure is a real bad guy in the Navier-Stokes equation. And the reason is that in incompressible flow, the difference with compressible flow, with all the other mathematical phenomena, the interplay between pressure and velocity is instantaneous. There is no time lag. You have incompressible flow, you put pressure in one end, the pressure is instantaneously filled at the other end and without attenuation. Okay? If you have compressible flow, you put pressure here, it takes some while to get here. If you have the mathematical theory of heat, you heat up here, heat propagates instantaneously everywhere, but with a big decay. When it's far away, it has very little effect. That's not the case with pressure in incompressible flow. Pressure instantaneously, whatever modification in the velocity is far away, it's felt everywhere through the pressure and the other way around. So I think this is what makes out of pressure the real problematic terms. So mathematically, the acceleration due to pressure is simply proportional to minus the gradient of the pressure. In other words, if pressure is constant, then the fluid does not accelerate, at least not due to pressure. You increase pressure here, then the fluid accelerates, so the fluid is going at constant.
So it's just minus 3D gradient of pressure. Yeah, that's fair. Like, again, I've seen these derivations. I have an idea of how this goes. Although I am being reminded of things that I just genuinely forgot in the years since the lectures, but
you add pressure here, then the fluid accelerates towards the area of lower pressure. Okay? And again, this is something that you can first establish sort of in bulk properties and then get the infinitesimal relation. But I'll discuss later, try to discuss a little bit about pressure, but remember that sort of the pressure induced, for instance, by the fluid, turning in a corner of the bottle, instantaneously is felt all over the bottle. So it's a typical example of an incompressible.
what is going on? Unfortunately, my headphones broke today because of my naughty cat, so I can't hear your voice. It would be great if you could respond through chat instead. What? What is going on? I am. Who are you? What's happening? Uh, I'm not sure what you mean, bro. I don't know if you actually cannot hear me. I don't know what the fuck you're on about. Okay, I'm gonna continue watching, to be honest.
Of the bottle instantaneously is felt all over the bottle. So it's a typical example of an incompressible thing is a train versus traffic flow.
Actually, yeah, hold on. That's a huge question. I don't know. This guy's asking if I played League of Legends, which I don't really. I've played before a bit. I'm probably like iron level, but I'm really confused, to be honest, what the goal is. What is he doing on Twitch if his headphones don't work? Like, I can't tell if he's just trying to talk to me or he just he left. Yeah, he's really just yapping. Okay, I guess I'll talk. Uh, he's asking where I'm from. Russian and Dutch. Yeah, that's a good. Who's this person? I think it's a bot. I can't create it today. What the fuck is it? Is this like new bot thing or is this like a genuine? Okay, I think this may be either a person who really has nothing to do or like I don't understand. Well, there are scenarios in which this could be a real thing, but like I'm sketched out by the text. Uh, sure. I mean, I don't see what can happen through a chat in Twitch, but like I don't know. In the modern world of language models, I am sketched out by any texts.
Traffic flow, there is a crash, the car coming behind slowly stop, maybe some can crash, but the fluid compresses. In a train, the train hits something, derails all of it because it has no room to compress. The car coming behind.
Okay. Okay. Graphic designer. I mean, that's cool.
Slowly stop, maybe some can crash, but the fluid compresses. In a train, the train hits something, derails all of it, because it has no room to compress, okay? If you ever try to fix a pipe in your home, you realize how incompressible water is. You know? That's why hydraulic systems are so good for moving objects or lifting weights, because you put pressure in the fluid. In an hydraulic jug, you put pressure in the fluid, and the pressure is felt in. They can lift 10 tons, 100 tons, right? I mean, just with a little bit of pressure you add in the other end, okay, because of incompressibility. Okay. So this is pressure. I think, for instance, in Navier-Stokes, let me give you some sort of reason why I think that pressure can be the culprit on creating infinite speed in Navier-Stokes. And I think sort of a visual effect you can take. Suppose you take this table. I used to play with pennies when I was a kid in my home. Many of you did, right? The bottle of pennies. You put pennies all over the table, and you pack them closely, so they are sort of incompressible, right? They're touching each other, right? And then I think that if you do that, and you squeeze the edge of the tables just right, you should be able to make the center of the pennies pop out, okay? And I think that's what could happen in Navier-Stokes, that the pressure from infinity can squeeze the flow just right to create a singularity inside. Now let me talk a little bit about viscosity. That is the good guy. Okay. So the other part of the Navier-Stokes equation establishes that the fluid is also accelerated by the drag that the surrounding fluid exerts on a given particle due to different speeds. Let me try to give you an heuristic idea of what happens. Okay. So suppose you have that the origin, at a given time, the particle at the origin has zero velocity. Okay. But the particles surrounding it are slightly moving to the right. Okay. Since the flow is viscous, that is, there is friction between particles, then these particles moving slightly to the right will push the particle in the center. We'll try to accelerate the particle to the right. Okay. And so in that spirit, then. So if you want sort of give a precise meaning to this idea of the particles dragging the flow, then what we should do is the following. You take a point, right? And you should take a tiny ball around the point, right? And you take in this tiny ball around the point, you take the average velocity, and you subtract it from the velocity of the point, right? And that gives you exactly the direction in which the fluid is accelerating the particle. So the acceleration due to the viscosity effect, in some sense, should be proportional to this quantity. The average velocity around a point minus the velocity at the point itself. Okay? And since the pictures clearly indicate sort of that this is a quadratic effect, right? Mm-hmm. This is a quadratic effect on the velocity field.
Fair.
This is a quadratic effect on the velocity field. If you want to get a quantity that is not zero, you have to divide this by the radius of the ball square. Now, you take the average in a tiny ball of the velocity, you subtract the velocity at the center, divide by the radius square, takes the limit, that gives you an infinitesimal quantity that reflects the drag that the surrounding fluid exerts in each particle. In fact, this is a very famous quantity. It's called the Laplacian. The Laplacian of the velocity is fluid exerts in each particle. In fact, this is a very famous quantity. It's called the Laplacian.
Okay.
The Laplacian of the velocity is exactly the limit of the average velocity minus the velocity at the point divided by the square of the radius. Okay? Notice that this choice of a measure of the drag that the particles exert at the point is not, is not to justify. It's just a choice. You could say, no, the drag may depend on the speed. I mean, if the points are going very fast, maybe the drag is bigger or smaller. If the velocity is sort of rotating in some special way, maybe the drag is different. So this is an ad hoc law. Okay, and so one could argue that, well, maybe this is the reason why Navier-Stokes equations doesn't work so well, because when the fluid becomes at high speed, who knows what happens with the molecules, right? They burn. Why should they interact the same way at high speed at low speed? Okay. Nevertheless, so this is the last term of the equation. Notice, let me point out that this is, in the vein of what I was discussing before, this is essentially an Eulerian concept. If you try to translate this to Lagrangian coordinates, it's a mess. That's why Navier-Stokes equation is usually written in Eulerian coordinates, because it's the least of two evils. The acceleration doesn't write so well, but at least the viscosity writes reasonably. The other way around, the viscosity becomes some very nasty expression. Okay?
Yeah.
So basically, I think by now I have described, let me write for you, then the Navier-Stokes equation. The Navier-Stokes equation says that the flow is incompressible in the Eulerian coordinates, divergence of the velocity equal to 0, and that the acceleration, which in Eulerian coordinates we have to write as Vt plus Vdv, is proportional to minus the gradient of the pressure plus the Laplacian, that is the viscous effect of V. Okay? So, so what is the expectation at this point? If we go back to the problem of the Battle of Hall, the expectation is that if you give me an initial velocity field, that if you tell me at time 0 what the velocity of this particle is, then I should be able to reconstruct the flow for all times. Okay? And so this is the option 1 of the problem. In other words, the problem has two possible solutions. Okay? And the Clay Foundation accepts for his money any of both solutions. So the first solution says, I give you a nice initial data, and you find for me a nice solution, a solution where velocity remains finite, acceleration remains finite, and so on, for all time. Okay? And as I said, this is a matter of internal coherence. It has nothing to do with the model reflecting reality. Okay? It has to do with the model being coherent. That is, that if you give me data, the equations at least have a nice solution, close to reality or not. Okay? Now, the other option that the Clay Foundation gives you is, okay, if you cannot do that, show us that the opposite is true. That you can find a solution, you give me a nice initial data, and you find a solution that starts very nice, and all of a sudden, at some time in finite time, it becomes infinite. Okay? Any problem with it? Okay, so these are the two options. Or you are able
Prove
to
it
solve the
this
problem
proof.
with a smooth solution for all times, or in finite time, the velocity becomes infinity somewhere. Okay? Now, what is known up to now? Well, what is known is that some sort of weak solution exists for all time. This was the work of Jean Leray, who I had the honor to meet. He died recently. He's one of the great mathematicians of the century, so I also have his picture. He constructed in the 30s basically a theory that included, he basically was one of the fathers of the theory and included the construction of weak solutions, to reasonable weak solutions to the Navier-Stokes equation. Okay? The second thing it is known is that if the initial data is nice, then these weak solutions, for a while, remain nice. In other words, the effect of the initial data lasts for a while. It's also known that after another longer period, due to the fact that energy dissipates, then the solution becomes small enough that it's forced to become nice again. Okay? If you think heuristically, the reason is that both pressure and the bad part of accelerations are quadratic functions of velocity. Now, if velocity is very small, the square of something small is much smaller. And so you can really prove that that's not bad for you, that you can control it. Okay? The problem is that in between, in the middle, in this period where the goodness of the initial data has disappeared, and still there has been no enough energy low, not enough dissipation to force the solution to be small. So there is this mid-range where you cannot prove that solutions remain smooth. In fact, you cannot even prove that the energy is the natural combination of energy, kinetic energy plus dissipated energy is preserved. You cannot even prove that. Okay? As it was mentioned before, we proved with Kohn and Nirenberg many years ago that in this unknown region, the set of points where the solution can become singular plus all its limiting points, that is, add to it all the jump you want, all the limiting points of the points you are considered, it cannot fill a curve in space-time. Whereas the halves of one-dimensional measure of that set is zero, which heuristically means that. It means that if a singularity appears at a time, it will not persist in time, it will disappear instantaneously. We cannot fill a curve in an instant of time, or any combination. That is, in the 4 dimensions that space and time are, the singularities are unable to fill a curve. So if singularities exist, they are really a very minimal set, physically sort of irrelevant, because you will never see them, it will not have any effect.
Okay.
Sort of what is my...
Set of points. Okay. It is known, Sikon Nirenberg, that the set of points where the solution becomes singular, so infinite velocity, or whatever, infinite acceleration, plus all its limiting points, cannot fill a curve in space-time, has 0 one-dimensional order of measure. So essentially that means that it is an instant in time or instant in space. Essentially, it can never be an effect. It's only an instant, as far as I understand what this means.
My personal belief, well, is the following, is that if indeed play option 1 is correct, that is that solutions remain always regular, this has to be attained because of a different approach. And sort of all the approach that has been taken with the Navier-Stokes equation up to now was to take ut minus Laplacian of u, which is a very good term. It's like the heat equation, is a very fast dissipation term, because viscosity dissipates energy very fast, and put everything else on the right-hand side as strict as junk. Okay? And so if you do that, there are many reasons, scaling reasons, there are a bunch of reasons that tells you that basically this result is optimal, that you cannot go beyond that. Okay? So if you just look at the structure of the equation at that level, heat equation plus a quadratic equal to a quadratic term, you cannot go further than this. You have to understand, I think that you have to understand it in Lagrangian coordinates. I think that the way to understand Navier-Stokes equation, if indeed solutions are regular, is because there are some concepts like the fact that matter doesn't penetrate itself, which is not transparent in Eulerian coordinates. In Eulerian coordinates, you have the velocity field, and if you want to reconstruct the position of the points, you have to integrate the trajectory of the points. Okay? In Lagrangian coordinates, the points are there. If, on the other hand, play option 2 is correct, that is that indeed there are singularities, well, there is a traditional way of trying to find singularities with simple structure, that is to find solutions which are called self-similar focusing solutions. Self-similar focusing solutions are solutions which at different times basically have the same structure but shrunk. For instance, a cone, if you take a cone in space and time with the vertex at time equal to 0, that's a self-similar picture. At every time it's the same circle that is shrinking itself, and you can make a dilation that is sort of the same value in space and time, and you get the cone again. Okay? So there is a tradition of trying to find self-similar focusing solutions. These solutions such as the flow at every time look sort of the same, squeezing and squeezing and squeezing, and at time equal to 0, a singularity will pop at the origin. People have tried that with what is called the Leray self-focusing, and it was proven by Nejas and Verac and someone else recently that that's not possible. So if you are going to find a singularity for Navier-Stokes, then I think you have to do a different scaling. You have to do an Eulerian scaling, that is a scaling that corresponds to the equation with no viscosity. And there is a way you can do that in such a way that the viscosity becomes a smaller order effect. And I think that's the only possibility I see in constructing a singularity for Navier-Stokes. So let me stop here. I'll be happy to.
Okay, so essentially, 2 options. One, prove that no singularity can exist or can exist. 2, prove that singularity appears for ordinary inputs. Can exist for ordinary inputs. That's sort of the vibe. Two options to solve it. All right. Let's see.
I think this is a shortcoming of the way the clay problem was set. I think it should have been set or in all of space. The clay problem is set in all space. But I think it's equally valid to solve the problem and equally hard to solve the problem in a bounded domain. Navier-Stokes has a natural boundary condition, which is called the non-slip condition, that the flow adheres to the wall of the container. So velocity is zero on the wall. So I think the problem should have been set that to solve in all of space or in a bounded domain with non-slip boundary conditions. So, but the clay problem is in all of space. You need a lot of oil to solve the clay problem.
Which is harder? Is it the same? Which
I
problem?
think philosophically it's the same. If you find a way to solve one, you'll find a way to solve the other.
Other questions? Yeah. Here.
Well, there is a very classical observation of Serring that if you take some vector field, like gradient of a harmonic function, some special vector field in X, some special velocity field, and you multiply it by your favorite function in time. Let me see if I have it. This is an observation of Serring that says take, for instance, 2x squared minus y squared minus c squared. This is a harmonic function. You take the gradient. So it's minus x, x minus y over 2 minus c over 2. So you take the gradient of any harmonic function, okay? And you multiply it by your favorite function of time. This is a solution of Navier-Stokes equation for all times, because everything is gradient of the pressure, okay? So this is a solution of the Navier-Stokes equation, which is driven by pressure at infinity. You see, instantaneously the flow, the role of the g of t is like you are controlling the pressure at infinity, and you do with the fluid whatever you want. You can do your g of t become infinite at some instant of time, which means that the fluid blows instantaneously everywhere, right? Now, you tell me, well, no, but I don't allow you that. I take initially data which is compact support. Well, pressure instantaneously travels to infinity. The pressure does not have decay. The pressure, if you start with velocity perturbation in a small domain, the pressure has very slow decay at infinity. It does not have exponential decay at infinity. So the interplay of what is local and what is infinity is very strange. So where is the truth? If it's close to this, or if it is close to option 1, I think it will only be seen when the problem is solved.
Fuck. Okay.
Yes.
I see the difficulty.
It's a different type of singularity because for compressible equation, the velocity, the typical singularity is discontinuous velocity. In Navier-Stokes, if the velocity is bounded, the solution is infinity. So when you talk discontinuity for compressible and discontinuity for incompressible, we are talking about different things. Okay, so, compressible discontinuity is a shock, it's discontinuous velocity. While Navier-Stokes is infinite velocity. Finite velocity for Navier-Stokes is infinite.
Compressibility, discontinuity is kind of fair.
Yes?
What's known about the lower dimensional version or higher dimensional version of this model?
Well, there is a two-dimensional version, which is flows which are planar. Not that lie in a plane, but that in every slice look the same. This is a very classical result that in 2 dimensions, Navier-Stokes solutions to Navier-Stokes equations are always regular. So in 2D, Navier-Stokes is regular, and it's a classical result. You can also deduce it from our theorem, because if you have a singularity, you will fill a full line. Yeah.
What happens when viscosity is zero?
Okay, that's the Euler equation. When viscosity is zero, that's without viscosity, that's an equation which is earlier than Navier-Stokes, which is called Euler equation. Euler equation, as Charlie Pfefferman points out in his presentation, is sort of an important, to understand it in some sense, may be an important previous step, because it's a simpler structure, and you want to know if in that case you can produce singularity.
Too easily solvable.
Solutions that indicate that the Euler equation is sort of much worse than Navier-Stokes, that doesn't have the regularizing effect of viscosity. But still, it would be very important to understand how infinite velocity can appear in 3-dimensional Euler, and see if that gives you a guide. In fact, that's what I think it should be done, to find a self-focusing solution for Euler, and then from there, sort of perturb it to Navier-Stokes.
But there is no money for it.
There is no money.
All right. Maybe it's time to think about refreshments. I remind you, 2 weeks from tonight, we'll have the 6th lecture by Dan Fried.
All right, people are kind of lame with their questions, I'll be honest. So to be completely fair, let's look at the actual formulas. Singularity as in velocity equals inf. Has been proven that the singularities into singularities if exist together with their boundary cannot fill a curve in space-time. My personal interpretation of what this even means is must be a straight line through time space. So 1D and 4D. Okay, cool. Let's quickly take a look at the formulas. Existence smoothness of the Navier-Stokes equation. The Euler Navier-Stokes equation describe Euler Navier-Stokes equation of the motion of fluid. These equations are to be solved on known velocity vector and pressure. Defined for position and time. Restrict attention here to incompressible fluids filling all of Rn. The Navier-Stokes equation are given by, so Laplacian of the velocity, change of pressure, some function of time is equal to acceleration and okay, it's not partial derivative, that's cool. And divergence equals 0, meaning incompressible. With the initial condition of initial position x at time 0 equals this shit, where it's given that is a given convergence-free vector field are the components of a given external applied force. Gravity V is a positive coefficient, the viscosity, and the Laplacian space variable. The Euler equation is set to 0. Equation 1 is just Newtonian law of force equals ma. Yeah. For a fluid element subject to an external force in time and to forces arising from pressure and friction. Friction, pressure. So this is the sum. This is F. And this is MA. So this is just A. And what is this again? Is this just the partial? Yeah, it's just the force F, the rising friction. Equation 2 says that the fluid is incompressible. Yes. For physically reasonable solutions, we'll want to make sure UXT does not grow large as x approaches infinity. Hence, we'll restrict attention to forces F and initial condition U that satisfy the shit for any n and k. Accept solutions 1 to 3 as physically reasonable only if they satisfy. Okay, sure. Then integral of square of this smaller than c bounded energy. Yes, essentially finite momentum energy. Alternative rule out problems at infinity. We may look at spatially periodic solutions. Thus, we assume satisfy. Okay. Jth unit vector. Cool. Partial derivative smaller than cm. Exception. Nice. Again, it's not that I understand what the shit is. I'm just kind of like getting the gist of it, and I will later research what that actually means. Fundamental problem in analysis is to decide whether such smooth physically reasonable solution exists in the Navier-Stokes equation. To give reasonable leeway to solve while retaining the heart of the problem, we ask for proof of one of the following four statements: existence and smoothness of the solution in three-dimensional space, a regular three-dimensional space, take velocity larger than 0, n equals 3. Oh, that's what the n was, I guess. Be any smooth divergence-free vector field satisfying. Take function to be identical to 0, force to be identical to 0. There exists smooth function that satisfy all of them. Z3 take this smooth, that's fine. 0 smooth solution. Okay, same, but breakdown. There exists a smooth divergence-free vector field and a smooth satisfying which there exists no solution. Okay, so you can just find an example or break down here. There exists smooth divergent-free vector and a smooth satisfying which is no solution. I am expecting to have to use AI for mathematics, by the way. Not that anyone cares, but just researching some of the stuff will be annoying. Let me sketch the main partial results known to regarding early Navier-Stokes equations and conclude with 3 remarks on the importance of the question. In 2-dimension, the analogous of assertion A and B have been known for a long time. Ledezhenskaya 4. Also for the more difficult case of the earlier equation. This gives no hint about 3-dimensional case since the main difficulties are absent in 2-dimension. In 3-dimension, it is known that A and B hold provided the initial velocity U satisfies a smallness condition. For initial data not assumed to be small, it is known that A and B hold also for v equals 0 if the time interval is replaced by a small time interval with t depending on the initial data. For a given initial U, the maximum available t is called the blowout time. Either A and B hold or else there is a smooth divergence-free for which have solution with a finite blowout time. For Navier-Stokes equation, velocity above 0, if there is a solution with a finite blowout time, that the velocity in one of the dimensions becomes unbounded near the blowout time. Other unpleasant things are known to happen at the blowout time if it's smaller than infinity. For Euler equation, if there is a solution with force equals 0, say, with finite blowout time t, then the vorticity satisfies integral of time. What the fuck is this? Integral of time. What is sub? Of vorticity equals infinity. Okay, vorticity goes to infinity at t. Many numerical computations appear to exhibit blow-up for solutions of the Euler equation, but the extreme numerical instability of the equations make it very hard to draw reliable conclusions. The above results are covered very well in the book of Patozzi and Maida, starting with Leray. Important progress has been made in understanding weak solutions of the Navier-Stokes equation. To arrive at the idea of a weak solution of a PD, one integrates the equation against a test function and then integrates by parts formally to make the derivatives fall on the test function. For instance, 1 and 2 hold. Then for any smooth vector, compactly reported in 2 dimensions of infinity, the formal integration by parts yields. Yes, I think I showed this. Note that the equation makes sense of u belonging to L2 FL1 L1, whereas it makes sense only if ut is twice differentiable. Similarly, if pi is a smooth function compactly reported, our parts imply solution to F19 is called weak solution of Navier-Stokes equation. A long established idea in analysis is to prove existence and regularity of solutions of a partial differential equation by first constructing a weak solution, then showing that any weak solution is smooth. This program has been tried for Navier-Stokes with partial success. Leray in the source showed that Navier-Stokes equation in 3 space dimensions always have a weak solution with suitable growth properties. Uniqueness of weak solutions in Navier-Stokes equation is not known. For the Euler equation, uniqueness of weak solution is strikingly false. Scheffer and Schindelman exhibited weak solutions of the Euler equations on R2R with compact support in spacetime. This corresponds to a fluid that starts from a rest at time t0, begins to move at time t1 with no outside stimulus, and returns to rest at time t2, with its motion always confined to a ball. Scheffer applied ideas from geometric measure theory to prove a partial regularity theorem for suitable weak solutions of the Navier-Stokes equations. Carfel and Karl-Nuremberg improved Scheffer's result and simplified the proofs of the results Scheffer Karl-Nuremberg. Source: the partial regularity theorem concerns the parabolic analog of Hausdorff dimension of the singular set of a suitable weak solution of Navier-Stokes. Here, the singular set of a weak solution U consists of all points in R3 such that U is unbounded in every neighborhood of the condition if the force F is smooth, and if the condition doesn't belong to a singular set, then it's not hard to show that U can be corrected on the set of measure 0 to become smooth in a neighborhood. To define the parabolic analog of Hausdorff dimension, we use parabolic cylinders, where is a ball radius r length, and then pk is the infinity of the infinite sum of cover e. I don't know what the symbols are. May be stated roughly as follows. Theorem: let U be a weak solution of Navier-Stokes equation satisfying suitable growth condition. Let E be the singular set of U. Then P equals 0. P1 E equals 0. Given it, it's just the bullshit. Given a divergence-free vector U and a force F satisfying 4 and 5, there exists a weak solution of a Stokes satisfying the growth condition in A. Beautiful. In particular, the singular set of U cannot contain a spacetime curve of the form. This is the best partial singularity theorem known so far for the Navier-Stokes equation. It appears to be very hard to go further. Let me end with a few words about the significance of the problem posed here. Fluids are important and hard to understand. There are many fascinating problems and conjectures about the behavior or solution of early Navier-Stokes equations. Since we don't even know whether these solutions exist, our understanding is at a very primitive level. Standard method from partial differential equation appear inadequate to settle the problem. Instead, we probably need some deep new ideas. That's what I'm here for. Again, I am entirely joking. I am not solving that shit. So here's the real question. Millennium problem 2. Would the solution of the problem, because I'm kind of interested in something, allow computation of currently impossible things such as turbulence, can I not spell turbulence? Towards a flow, etc. If not, what is the main benefit of solving the problem, aside from purely nice math? I feel like that's a valid question because as an aerospace engineer, I would love if solution actually help deal with fucking turbulence. Although I'm a space engineer, I got away from turbulence. Forms and imperfections whether Okay. No, it will not allow to solve. Yes, CFT is the way. Oh, cute. That's a cute simulation. I don't know if it's good actually. Okay. So the main problem asks about mathematics. Mathematicians to prove or disprove the given smooth initial state equation will always produce a smooth, predictable flow forever. The alternative is that the equation can reduce to singularity, a point where the velocity or pressure of the fluid reaches infinity. If a singularity can exist, it means the Navier-Stokes equation do not perfectly describe reality at microscopic scales. Just as general relativity breaks at the singularity of a black hole, telling physicists they need a new theory for quantum gravity. And if a Stokes singularity would tell physicists that our fundamental model of fluids is incomplete and that we need a new theory to describe fluids. Okay. Before diving into the mathematical benefits, you can experiment with how currently handle fluid dynamics uses relation. Adjust the Reynolds number below to see how the flow transitions from laminar to turbulent. Yeah, okay, this is pretty shit. When running complex CFD simulations of turbulence, the software sometimes crashes because the math creates artificial infinities blowups. Right now, we don't know if these infinities happen because the code is flawed, the grid isn't fine enough, or is the equation themselves actually dictate the infinity value at the exact spot. If mathematicians prove Navier-Stokes solutions are always smooth, meaning infinity is impossible in reality, it gives software engineers a strict mathematical boundary. It tells them if your simulation crashes, the equations are fine, your algorithm is the problem. The mathematical techniques used to prove the millennium problem would almost certainly be used to build better, more stable CFD algorithms that are mathematically guaranteed not to crash. Okay, so we can improve CFD. Demystifying the energy cascade, turbulence is essentially large swirling eddies breaking down into smaller eddies, which break into even smaller ones, transferring energy down to the microscopic level where it dissipates as heat. This is called the energy cascade. We understand this conceptually, but the mathematics behind it is incredibly murky. To solve the millennium problem, mathematicians will likely have to invent entirely new fields of calculus and topology to track how energy moves through these shrinking vortices. Those new mathematical tools could finally give physicists a rigorous analytical framework for understanding exactly how turbulence works, rather than just relying on approximations. Okay, fucking I know both. This is gonna be tough. Okay. Brother Stokes, why did you steal Navier's stuff? Let's see the Princeton lecture. Is this the same? No, it's way later.
Very happy to be given the opportunity to introduce the first speaker, and who's going to talk on one of the topics of one of the Clay Millennium Prize projects. Peter Constantin was educated at the University in Bucharest and did his PhD under Shmuel Agmon at the Hebrew University in Jerusalem. After a long and distinguished career at the University of Chicago, he moved last year to Princeton, where he was Will Martin and junior professor in the mathematics department and director of the program of applied and computational mathematics. Over these many years, Peter, through his work on numerous aspects of the rigorous treatment of fluid mechanics and in particular turbulence, has been inspiration. It's a great pleasure to introduce him and ask him to give his talk on Navier-Stokes equation.
Thank you very much. I hope you can hear me. I'd like to see
the board. It's a great honor for me to be invited to speak here, in particular in view of the great occasion we are celebrating the opening of the Math Institute. And I think that I'm both very pleased because I see with this occasion we have, and I would like to thank the Clay Foundation for facilitating this. We have a wonderful workshop on problems related to the Navier-Stokes and fluids. And I think that, in some sense, that justifies all this endeavor. We are here to do math, and that's what this building is about. So I talk about Navier-Stokes equations, and I'm imagining an audience of mathematicians, but not necessarily, although I see some of my friends here, I'm imagining that some of you might have wish to forget some of the analysis. So I will try to remind you some of the basics. I have a little bit of recommendation about introduction. I was, because you mentioned the fact that this will be accessible to all. I'm hoping it will be accessible to all mathematicians.
That's what I meant.
So here is the problem. Let me put it up a little bit, and then I'm going to explain each term. Okay. So these are Navier-Stokes equations. I also would like to refer also to my colleagues, the people who are actually experts, take the workshop and so forth. With a little patience, at the end, I will give them something. This is, after all, the name of this meeting is a research conference. So at the end, I will give them something that is new, fresh, by new, I mean order of months, and I put it on the archive maybe 2 weeks ago. So the problem, let's see. U is a velocity, and it is a function with values in R3, so it has 3 components. It depends on 4 variables, x in R3, and time. Time is non-negative because of the way things are. You'll see in a second. This equation is the momentum balance, it's Newton's law. And here the first term is the time derivative of u, which is the acceleration at the fixed point x. This term is a first order derivative, so this little triangle is a derivative. In each direction, so you have 3 directions, and this dot product means u1 dot d dx1, u2 dot d dx2, and u3 dot d dx3. So it's a vector field differentiating u itself. So this is if you want, these are 3 equations written here. Okay. Nu, and you'll need to remember that, nu is a number, and it is the kinematic viscosity, positive or 0 number. It has units of, let's say, length square over time, so 10 meters square per second. If you want a normal temperature in this room, maybe about 10 to minus 2. This is the Laplacian, Cartesian Laplacian.
Thank you. I really appreciate this. I was really thinking. I feel nervous about this new series because this is really fun. Like I don't know how long I will last actually trying to solve stuff, but I kind of just feel like putting like 100 hours into it. Like I think if I stream consistently every week for a couple hours, and I'm here for what, like 20, 30 weeks, 5 months, I could get to 100 hours, possibly. And I would like to. I would like to become not an expert. 100 hours is not enough to be an expert in the field in this. I would like to understand the problem very well. And the reason these millennium problems exist is because mathematicians not gave up, but they were like, hey, we've tried every trick in the mathematics book and it doesn't work. We need an entirely new approach. Someone, like, please pay attention to this, try new stuff. So I want to be a part of this. Yeah. But I want to make a YouTube video out of it. It's scary because it will be kind of boring, but I think it would be interesting.
In each direction, a trace of the Hessian. So you have a second order differential operator in x. This is derivative in time. This here is the gradient of pressure. It is a physical pressure, but it's not the hydraulic pressure that you can imagine that you learned in high school from Torricelli and things like that. It is a...
Yeah, it's really boring. I fucking muted it instead of... Okay, my bad. It's boring. Okay, it's boring to watch, and it could be for like you or like YouTube, right? Generally, like it's just theoretical mathematics. It could also be boring for me if I realize that I genuinely like can't handle it. But it's really interesting because if I manage to even just understand what's going on well and like be able to read like a late research paper, and I'm not even speaking if I manage to like have an idea, solution is not happening, but like an idea of how the solution could work. Um, that would be so exciting. Like me just understanding what I'm talking about on this topic would be so cool. I want to post it on YouTube because I am inspired by my beautiful girlfriend who is a YouTuber and is so beautiful and so amazing and so fun. And I actually always wanted to post things on YouTube and I always wanted to stream, but I always felt too scared because I am a pussy. Um, and the combination of my brave girlfriend, me having way too much free time, technically, and watching too many Ludwig videos of if you want to stream, just stream and do your own shit. And if people don't like it, doesn't matter. I have decided that it's time to sink a bunch of hours into doing random stuff. I'll be sometimes playing Minecraft. I'll be spending the rest of the time doing this. If I solve it, I pay my parents' mortgage. That's kind of the vibe. I'm not gonna post lives. I'm gonna edit them in the end into a single video, like after the internship. But I might make like a small videos on the way. Like imagine I make a video of like solving from scratch and I give like cuts of this live stream essentially. And then I post it and I'm like, oh, join on stream. I'm like streaming it now. And then if it like in the end I make a summary one in addition to that. That's what I might do. But again, the thing is to make a video about it, I would like some conclusion. So I can't just dilly daddle for 100 hours and then say done because that's worthless both for me and content wise. So my idea was to at the very least write a paper on summary of approaches and dead ends and like either write like a short paper that summarizes the current humanity's attempt at solving this or come up with some other like this is just the thing that I came up with that I could do even if I don't manage to achieve anything at all in any sense. But obviously if I see any like if I ever have an idea of how I could try, the end of the video could just be proving that my idea is stupid or something. But like I need I need a goal. I can't just watch videos about the problem and read articles and that's it. You know? Yeah. I'm probably gonna finish this video and go to sleep, by the way. Like the stream is gonna end when I finish this video. Good luck. You got it. You got it. Come on. Tomorrow we'll play Minecraft and I'm gonna stream that too. So feel free to leave the stream open or be here with me. I would love nothing more. But yeah, this is how the life goes. For me. Bye. Fuck. Back to watching Navier-Stokes equation videos.
Cartesian Laplacian two derivatives in each direction, the trace of the Hessian. It has units of, let's say, length square over time, so 10 meters square per second if you want, a normal temperature in this room, maybe about 10 to minus 2. This is a Laplacian, Cartesian Laplacian, two derivatives in each direction, the trace of the Hessian. So you have a second order differential operator in x. This is derivative in time. This here is the gradient of pressure. It is a physical pressure, but it's not the hydraulic pressure that you can imagine that you learned in high school
Yes.
From Torricelli and things like that. It is a force, because after all this is Newton's law. Acceleration equals force. Mass is 1 here. The density is taken to be 1, so everything.
Let's see where this goes.
So this is an internal force, a force that keeps the fluid from breaking apart and maintains this other constraint here, which is the divergence of the vector field being 0. Divergence means v1 directional derivative in direction 1.
A lot of this is repetition of stuff I know, but like yeah, this is all the definition of a Navier-Stokes equation. my goal is to spend many hours researching it, and I'm gonna throw shit at the wall and hope something sticks. It's very curious. I'm very curious to see how far I can get spending in large double digits slash low triple digits of hours as an aerospace engineer with no actual experience in complex aerodynamics or mathematics. How far can I get with solving a millennium problem on fluid flow? I don't know what's going to happen. I'm going to see.
One of component 1 plus the 2 direction derivative in direction 2 of component 2 and plus the 3 using. So this is the tangent of the fact, so in other words, this whole description here, if you want to do a description at the tangent space of an infinite dimensional kind of group of transformations. So the statement that divergence is 0 is really the tangent to the statement that volumes are not changed under this group of transformations, a group of volume preserving diffeomorphisms, and this is the statement that at the tangent you are preserving volumes. So this problem needs boundary conditions, and we're going to not talk about that because that's complicated, so we're going to imagine this to be decaying, so the velocities are going to flop to 0 at infinity, or we pretend things are periodic in this talk. And boundaries are extraordinarily important, and after all, they're situated at the boundaries. And we have to supplement this with boundary conditions I mentioned. We have to supplement it with initial conditions, what happens at time equals 0, because I said time is non-negative. There is an arrow of time here, and the arrow of time goes one way. Has to do with this little pesky coefficient viscosity, because we have, if you ignore the nonlinear terms, which are this guy and this guy, the u dot grad u and grad p, you have the parabolic equation, and that has an arrow of time. And that is a reflection of molecular mixing, molecular diffusivity. This term here, u dot grad u, together with the time derivative, it's called the material derivative. So this expresses actually time derivative along particle trajectories. You can imagine the flow moving, and if you, instead of sticking a point in space and letting the flow, observing the flow past that point, you can label your original position and move with the flow, and then the combination of these two things is the time derivative along that particle, so it's the acceleration on that particle. But viewed from a point in space, this thing looks non-linear, okay, and it is non-linear. So that's the equation, and the problem is
The Lagrangian approach is nonlinear.
is to study this equation, its smoothness of the solutions of this equation for large initial data. And I have here an EG. So let me give you two kinds of examples, okay? For a moment, let's imagine that we are in Umbria, okay? There is a beautiful mustard field, okay, in the spring, okay? A few poppy seeds here so that you can see some nice colors. We are on a highway, but the highway is empty. We are allowed to green here, okay? Highway is empty, and then there is a fast-moving car. And again, we are allowed to green. Say, let's say it's a Lamborghini. And it moves like 200 kilometers an hour. And there is nothing else, okay? This creates a flow because I moved something and there is a resistance in the air and things become kind of like agitated. And these are essentially the realistic boundary conditions that we're not talking about. But you can imagine them also as an impulsive initial condition. So you have a velocity, if you are, let's say, within 10 meters from the ground, you have a velocity of about 100 kilometers an hour at time 0. The thing passes, and then things will settle down. Okay? So that's really a large initial data. Another large initial data might be this. So you have a large vortex, and this is in Kansas, I think, where Toto and Dorothy are still in Kansas, I think, at this moment. And you're seeing a incipient tornado. Now, of course, the Navier-Stokes equations, the way I described them, they ignore a lot of details, and this is really not a complete description because there is moisture, there is a lot of other stuff going on. Okay? So at this point, you might think that this is going to be a very cute talk with lots of pictures, and those who know me know better. So I apologize, it's not going to be a cute talk. So this is the end of the pictures. So I'm going to motivate a little bit the issues with some elements that come from turbulence. Turbulence is a very important endeavor. It has practical applications. It has attempts to theory. It is one of the hardest nonlinear problem, and it is hard because it is at human level. So many of the problems that have essentially a balance of scales and that have to do with intermediate scales where we live, they're very nonlinear and very difficult. So I will mention a few things about turbulence, and in particular, I will mention a little more mathematical things about anomalous dissipation, and then I will describe elementary properties of the Navier-Stokes equations and Euler equations as we know them. And as I said, for those patients interested in something relatively new and who know the equations, I will show some computations and some formulas for the pressure. The pressure is a very important thing in this turbulence field and in Navier-Stokes. And then I will end with a few words about output, in which I'm going to move away a little bit from the Navier-Stokes equations and a couple of maybe open directions. So, turbulence. Then I'm quoting from a book by Yuri Altrich, who's a friend and a good theorist who spent his entire life working in turbulence. And the book is called Turbulence, and the legacy of Kolmogorov, and it is a wonderful book. So these are supposed to be experimental laws. So the first one you can read essentially says that if everything is kept the same, except for viscosity, which is lowered as much as possible, it's a theoretician. Okay, so I'll explain that one in a second. The energy dissipation of mass behaves in a way consistent with the proven mass, with a finite positive limit. So I said it's a theoretician because you don't lower the viscosity very easily because viscosity is a material property of the object, but you can change other parameters, and you'll see the Reynolds number in a second, so that effectively you lower the viscosity. Numerically, you can lower the viscosity. So here is the energy dissipation per unit mass. So the dissipation word means that I take minus. Okay, so if the rate of change of the energy is negative, and this becomes a positive quantity, this is a Kolmogorov notation. Epsilon is not necessarily small, and the statement is that epsilon is positive. Now, the energy is measured in an average sense. So you have here, let's say, for now, a Q, which is the unit box in which the things are periodic. So unit period box. Please unit would be R3. So you take
Go the
the
screen.
size of the box, or the volume is that Q, and
Okay.
1/2 of the kinetic energy. This is the average kinetic energy. And
I
so we
hate
have
it.
this Stokes equation, exercise number 1. If you are allowed to do everything that you would like to do, integrate by parts and so forth, you get that this is equal to the average gradient squared divided by L and so forth times this C viscosity. So now let's read this again. Finite positive limit, mu goes to 0. Well, I have a product of two numbers. The limit is positive, 1 goes to 0. So maybe something becomes big here. This gradient in velocity might have to become big. Okay, in one way or another. The second law is called the two-thirds law. This is the following. Again, keeps proving. I will explain the Reynolds number in a second. The higher Reynolds numbers, if you take the velocity increment, I'm sorry, he wrote, and I wrote it with notation V, it's our u. Okay? So that means I take u here minus u there, and the distance between here and there is L. Actually, you project on the direction of L, but that's not very important in this vague description. And if they're separated by distance L, then the expected behavior is two-thirds power. So I explain here what the Reynolds number is. The product of the typical velocity, well, typical velocity maybe is the mean square velocity. A typical length, in the case of the Lamborghini, it was like 10 meters. In the case of that tornado, was a couple of hundred yards. And this one, okay? The Reynolds number is the most important parameter, one of the two important parameters in turbulence, and if Reynolds number didn't exist, we couldn't do experiments with wind tunnels. So the Reynolds number allows you to actually, it reflects the scaling properties of the equation, it allows you to actually scale down things, make an experiment at a certain scale, and infer things about larger scale. So it is, Reynolds number characterizes the regime in which you are. So the statement that this goes like, we have is essentially turbulence, and this epsilon is the same epsilon from here. So
I'm really
in
mad
turbulence,
at
the
quite
statement is
from
that
the show.
for two-dimensional analysis, if you think
This is
about
making
the
it
epsilon being
useless
the
for
rate
me.
change of energy, that's L squared over T squared by another T, L squared over T cubed, and then you multiply by another N, it becomes L cube over T cubed, and you want it to be a U L over T squared, so they go to two-thirds power, they can do that. Okay. This is supposed to happen in the inertial range, which means not really to L to 0, but for L larger than some cutoff. The consequence, or an equivalent way, is the famous Kolmogorov spectrum, which is kind of a Fourier transform of this, in one dimension and correlations, but never mind, that says that the energy behaves like wave number 2 minus 5/3, and that's the same thing as this 2/3 here, and again, epsilon constant, all is done by dimensional analysis integration, insisting that there is only one dimensional parameter, and that is it. The only
Oh
one-
my god, my fucking god. Whoever filmed this, I want to put their head on a steak and like bite of it as if it's like one piece drumstick, and I'm Luffy after a battle. I just want to go. Because what the fuck was that? This is I understand this is like a popular science thing. Also, quality is dog shit for 2013. They already had cameras. Fucking, when did Interstellar come out? Like 2016 maybe? Like fuck off. But also, it's a mathematics lecture. Show me the formulas. Don't be an asshole. I had to listen. Obviously, I don't get shit when I listen because he's not reading formulas. He's just saying stuff. I know what Reynolds number is. I just want to turbulence flow to a high Reynolds number. The mean square velocity increment between 2 points separated by distance L because approximately is 2/3 power of the distance. Is it actually true? That's so funny. A very high Reynolds number is an interesting definition, though.
that has dimensions is epsilon, and then if you're talking about wave numbers, they have dimension of 1, right? And then things come out. So the Kolmogorov spectrum.
Kolmogorov. I also know Smirnov-Kolmogorov statistical measure. Well, the Kolmogorov guy has done a lot. Russia used to be good at science.
Also has a cutoff as opposed to decay like this up to KT. And KT is the cutoff where viscosity enters. And at that cutoff, you see again epsilon, but you see now that the viscosity becomes very small, this KT goes to infinity, or L, this L goes to 0. So in some sense, you are taking this log to asymptotically become valid for all L, or this log asymptotically becomes valid for K. So there is a cutoff, this is cutoff at the end, tiny n, and then things become analytic, smooth, and so forth. So that's
My
those
brain
are
is hurting.
experimentally verified to a very large degree. So the quality of the experiments, turbulence people like to fight and they complain to each other about various details and so forth. By comparison to other experimental areas of physics, the quality of the agreement in the power laws is outstanding. So they fight about minor details. But, so if you look at power spectra and ranges of for instance, for the Nusselt number versus Rayleigh number, there are like 13 orders of magnitude of agreement. So it's behooves us to explain this, okay? So here are some questions. Is the implicit of zero? Is the implicit of this product zero?
Back to lower speed.
Or not zero, I write it in a different way. Is there a viscosity independent, positive, energy transfer rate in the inertial range? So inertial range is this range of wave numbers, and you can think of the energy, you can Fourier transform the thing and truncate at k and ask yourself, is there a transfer from k to higher k's that doesn't change with k? In which case I will have non-dissipative, I will have dissipation of energy non-zero. The big problem is the velocity Navier-Stokes solution smooth. Is the zero viscosity limit of the velocity relative continuous with exponent 1/3? That's this two-thirds law that Frisch mentioned as being a law. Is the implicit limit of the equations the 3D Euler equations, or an energy dissipative version of the 3D Euler equations? So these are ambiguous questions, and I mean by that, especially to my friends, there are versions and the caveats, and you have function spaces, and certain things are not really, you can get both answers if you ask it this vaguely, but they are fruitful questions. So, and now maybe there are some engineers and real physicists in the audience. I'm going to be a little bold here.
Engineers mentioned.
So, and now maybe there are some engineers and real physicists in the audience. I'm going to be a little bold here. I think the analysis generates ideas that are relevant. And they're relevant to complex fluids with industrial and biological applications. If anything at all, at the minimum, they'll give you better ways to compute. To weather and climate, to fluid structure interaction, by which I mean actually having fluids interacting with flexible boundaries, which have engineering and biological applications, to astrophysics, MHD, that's magnetic hydrodynamics, plasma physics, and energy. So they are actually making progress in analysis, in pure analysis, is going to impact direct important applications. So there. Okay, let's talk a little bit about the number dissipation of energy. So there are two ways to pass through this limit. First of all, we can fix time and chunk of time of our choice, and then let this viscosity go to zero, and ask ourselves the question of dissipation of energy. If you formally take nu to zero, you get an equation without that Laplacian. Okay, because mu is zero, it multiplies the Laplacian, that is gone. That is called the Euler equation. It's older than the Navier-Stokes equation. It actually is due to Euler, and it's, we'll talk about it very soon. So there is a conjecture by Onsager. Now, our Onsager conjecture is a few years older than Kolmogorov's spectrum, Kolmogorov's spectrum, but they didn't know. He didn't know about it. And the conjecture is in some sense related to that. So the conjecture says that if you take Euler equation, no Laplacian, no viscosity, the solutions will conserve energy if the solutions are smoother than C13. That means a third of a derivative. For analysts, we know how to take fractional derivatives. One way of thinking about it is you already took one when you saw the two-thirds law of in the description of Frisch. You take differences and you ask differences around a scale L to scale like L to 1/3. So if they're smoother than 1/3, then solutions conserve energy, and the conjecture keeps going and says for less than 1/3 smooth solutions, there will exist CS solutions for which energy is dissipation. So the first part has been proved to a large degree, in the sense that if you go, this is a funny space, it's a world record space, but this has been done in stages by Gregory Hay, by Renata, Titi, and myself, Lucien Robert, and then a bunch of friends more later. This is a complicated space, but let me say, L3, we're going to encounter this, and I don't, these are LP spaces, so you take the object and raise it to the third power and integrate in time. And the object is the norm of the function in this crazy space. The 1/3 is this 1/3, so it's a third derivative, and then there are some limits that, if you don't know what they are, forget about them. But they say, if you are a little better than 1/3, very, very, very little better, that's what all these readings mean, then the energy is constant. And this is the easy part. The hard part is to find solutions that do not conserve energy, and those first examples were given by Daniel Scheffer. Then the Schneermann produced solutions in L2 that dissipate energy. Scheffer proved that you can start from nothing, have something, and then nothing again. So then total non-uniqueness of the solution. And more recently, the last, let's say, 5-6 years, there is a very great improvement of the situation. So there is work by Delevitz and Sekheidi, who went to various CS spaces by using complex integration ideas, H principle, and diminishing of nonlinear fluxes. So these are H principles, a number of ideas that go, conjunctions of ideas that go back to Nash and Gromov, and the school, Schwerak, and school of people who do complex integration. So the current world record is 1/5, a little worse than 1/5, and this is due to Phil Isaac, who's graduating from Princeton and moving to MIT. And his additional idea was this material derivative, as mentioned, time derivative along particle trajectories, is better behaved than the time derivative. And that improves things. Delevitz and Sekheidi were about 1/10, and then the situation is 1/5. There is a long way to go between 1/5 and 1/3. Very long, because the new idea. Okay. So that was if you fix time, and therefore you take viscosity to 0, and if there are no boundaries, periodic boundary conditions, let's say, then you end up with solely Euler equations, no Laplacian, and then that's what's going on. The other order is to take time to infinity first. That's appropriate for experimental situations in, let's say, finite region. So you can imagine, some of you may have actually participated in these things, the Taylor-Wade experiment in which there are concentric cylinders, one is rotated, that's how we impart motion to the fluid. That's like a Lamborghini, except that it's a whole fleet of Lamborghinis and they never stop. So it's a shear-induced motion, and then you swirl that thing. The motion, you look, they have nice plexiglass walls, you look at the fluid, you see a sea of bubbles that doesn't move anymore, and that is a permanent regime. Long time here. Or you can look at a Rayleigh-Taylor convection in which you heat from below a pot, cool it from the top. There is a lot of motion, heat, supply heat constantly. After a while, you reach what's called the permanent regime. And that is why you are in a certain regime in which the non-slopes are forced, it's a fixed force, fixed viscosity, and you wait till things stabilize more, but do what they do. And only then increase the speed of rotation, get the Lamborghinis to go faster, heat a little stronger, and see the limit of u goes to zero. So this is described by selective stationary statistical solutions, by which I mean you take a solution, I forgot what the initial.
So basically, you can reach a T-infinity static solution. Okay.
You take a solution of the Navier-Stokes that fix mu, you take a long-time average, maybe measure it with
Statistically static, so dynamically static, not just static.
Then you record that, take very long-time averages, and only then take the limit to zero. You get a measure,
Yeah, like stationary average.
And this will end up by being an implicit statistical solution. Now, that's not the same as taking the initial value problem for short time. There are many more initial value problem solutions. This might select certain solutions, okay? The whole case, okay? So then another dissipation, for instance, of energy would be that in some average sense, the quantity that's supposed to stay positive after a long-time average stays positive. All right? In fact, that is, again, the non-vanishing of flux of energy. So we need to make sure that we understand that we're talking about transfer of energy to high frequencies and not just this quantity, because there are situations in which you can make this quantity go to infinity, there is no transfer of energy. So bounds for epsilon is an open graph. So now I'm going to come back and remind everybody some of the basic facts about Navier-Stokes.
Basic results.
So there exists global weak solutions to finite energy of 3D Navier-Stokes equation. This is a result of Jean Leray around 1934. So global means global in time and also arbitrary initial data in L2, square integral. Weak means the solutions satisfy the equations, let's say as distributions. Okay, find out if test them with something integrated. So they are not classical solutions. Existence, uniqueness, and regularization, or in other words, smoothness of global solutions is done in 2 dimensions. This is a long story. I cannot actually, and I apologize to all my friends, I'm going to refer to all kinds of results. I cannot quote everybody. I'm hoping that I'll be forgiven. The same thing is true in 2 dimensions for Euler equations, no Laplacian, which is a, let's say, harder problem. Smooth solutions to exist, and I made the phrasing a little different here because here, if you start non-smooth, you become smooth instantaneously, and that's why I say weakness and regularity. Here, you start smooth, and then stay. If you have small data, small Reynolds number, in appropriate set, then the 3D problem is exists global smooth solutions. For Euler, 3D Euler, there is solutions only for short time, smooth solutions for short. And a basic balance is the energy balance. If there are no forces that stir the fluid, energy at time t is less than the energy at time 0. There is no increase in energy. And
Global solutions for small data in 3 dimensional Stokes, local existence, and uniqueness, smooth solutions of 3D Euler. Okay, cool.
And the rate of dissipation is as we saw with the negative So, what I can do our problems more precisely, let's say, let me put them both down. So, you fix initial data, let's say that you are periodic or you are C0 infinity or decay, then your contact is supported and infinity smooth. Initial data, let's say, in order to make them divergence free, pretend that they're curl of some smooth vector. And then the question is, does the solution of 3D Euler, here is 3D Euler, without the Laplacian, with that initial data exist for all time and remains smooth for all time? And then play problem, does the solution of 3D Navier-Stokes equation, the same initial data here is the Laplacian, exist for all time and remains. So for Navier-Stokes, we have parameters, so if mu is given, then you ask the question for all you know. Okay, smooth enough, C0 infinity, but all. Now, the 2 problems are related and different. Now, I'm going to start talking about how to graph these problems, and I'll start with some things that make them related, a way to graph them in a way that looks they're related, and then I'll mention some differences. So at this point, where if you are friendly on the angle becomes a little wandering, we're going to go up a little bit angle. So, related. First of all, there is no result of Kato that for short time Euler solutions are smooth, and there is no result of mine that for a long time, if you fix initial data and the time, and if you know that the Euler is smooth up to that time, then for the same initial data, Navier-Stokes is smooth, provided the viscosity is small enough. And how small depends on time and on the entire Euler solution. So in particular, there is a gap between small viscosity and large viscosity. For small enough viscosity, depending on all these parameters, we know regularity. For
basically, yeah, as the stuff that was mentioned before, that like when time is very small and there is small forces, then it's smooth at low viscosity. When time is very high, energy has dissipated, so they have low energy, so it's smooth again.
Large enough viscosity, we know regularity for all initial data. So that is small Reynolds number. and there is this gap which I think is quite artificial and needs to be filled, because that would be a weird situation in which you have, but maybe not, because there's not initial data per initial data accounting here. There is a deeper relation, because I'm talking about relation, and the deeper relation has to do with vortex dynamics, division of nonlinearity, and vortex reconnection. So I'll mention a few of that. So the vorticity is the curl of the velocity, so that the antisymmetric part of the gradient. And it has an equation. You take the gradient.
The fuck?
So the vorticity is the curl of the velocity, so that the antisymmetric.
I like how it. He definitely did not say anti-Semitic, but it is kind of interesting because he got his PhD in the Hebrew University, Jerusalem. Do you think subtitle AI considers this, or is it just sound? Does he?
So I'll mention a few of that. So the vorticity is the curl of the velocity, so that the antisymmetric part of the gradient.
Anti-symmetric.
And it has an equation. You take the gradient of the differentiate the Madison's equation. The pressure disappears. You have a piece here. Here is a material derivative. In other words, there is transport here of the vorticity. Here is Laplacian, and there is this term here, which is a very natural geometric term. It's not just an addition to the right-hand side, as many people in engineering and math think. It is actually a very natural term that gives you some conservation of circulation. But it is absent in 2D, and that's why 2D, everything is fine. And it's present in 3D. So there is no blow up in 2D because this guy is not there. And in 3D, this is really essentially the problem, and this problem is with or without viscosity. So, and also physically the issue. So, vorticity is law. I'm going to give you we're going to try to grab this problem 3 times. And each time I'm going to say this law, because it is law, there are criteria. So, for the Navier-Stokes equations, if you knew that the L2 norm meaning integral of the square of the thing, to the 4th power, so integral of the square of the thing to 1/2, so that you make it in the thing. So, only make it 4. To the 4th power in time, if that was finite, and by finite I mean finite, I don't know how finite, it doesn't have to be smaller than something, just finite. Then the solution at every angle of the solution is smooth. What is known, the order in which I do this are the conditions. So for Euler is the famous Biel-Kaplan-Meier theorem that says, from the 70s, that says this is essentially due to the array. I mean, I cannot give a reference. It's the easiest to show a criterion. And everything can be traced back to this. So Biel-Kaplan-Meier for Euler, it's a different quantity, different homogeneity. It's a stronger assumption in some sense. And if this integral, the integral in time of maximum, this anything, maximum vorticity, if that is finite, then the solution is easy. What's known? For Euler, nothing. For Navier-Stokes, again, this goes back to the array. The integral of gradient u squared and the integral of omega L2 squared are the same thing. So this is a dissipation of energy. Okay? What is the story about the division of nonlinearity? Let me go back a little bit and remind you of this term. The reason why this term is absolute in 2D is geometric. Omega points up, and the velocity depends on variables on the graph. So the scale of gravity is 0 because of geometry. Omega is a vector that's parallel always to the same direction, the direction perpendicular to the plane of motion. So 2-dimensional motions are motions in a plane, and there is a perpendicular vector. So that in particular direction of vorticity is constant. So Challenger from 20 years ago had a theorem that says, generalized in some sense the 2-dimensional situation, and looked at the directions field of vorticity. So the vorticity normalized and creates a unit vector, and if this is smooth in regions of high vorticity, so it doesn't have to be smooth where the vorticity might have trouble being defined there, then the Navier-Stokes solution is easy. And this has been improved over the years by a number of threads, removing the smoothness here. So we asked for Lipschitz and it's further enough and so forth. And recently by Rich, who did actually a very interesting combination of coherent patterns and the criticality of the equation. I cannot get into that. And at our workshop here, I learned about the work of Professor Giga and his collaborator, and I haven't seen the preprints, so I hope I'm having the right collaborators, where he studied this problem with boundaries. And that's a big change and a difficult improvement, but essentially the conclusion is the same. So you have vortex reconnection is a regularizing mechanism. So this is like this. What happens, let's tell you the story. There is a story. So strong coherent vortices form. So what that means is if you look at the field of vorticity and you paint in only the regions where the vorticity is more than 90% of its integral of the maximum, right? So more 90%, let's say, than the L1 norm, okay? The L1 norm in Navier-Stokes actually is not increasing, so it's a very good way of quantifying this. So we look at that, and then people have actually numerics, and then what do they see is tubes, intense tubes of vortices. And as they stretch, because of circulation, as you know from
they've ripped the smaller ones.
There is a conservation of circulation. The shorter the closed path of velocity does, the faster it has to move. They stretch, become coherent and straight, intense, narrow vortices, and they approach. And when they approach, they violate the smoothness assumptions because they would have the gradient in space of the direction go to infinity there if they would cross. But they encounter the viscosity, and there is a bound, a weak bound, that relates the viscosity, the magnitude of the vorticity, and this gradient of psi. And it says this integral spacetime is less than the budget of energy that you had originally. So this says the viscosity wants this guy to be finite. When they approach, they reconnect, by reconnection, we mean that one arm goes with another arm. Essentially, they do one of these chromosoidal things, move apart, and then they hit. Okay, the reconnection is a topological change. It's not allowed in the Euler equation, but it's perfectly allowed and happens a lot in viscous fluids. And this happens several times, and if you don't force it, the thing goes up. So this is a scenario. It's not a theorem. Okay, the theorems are an L infinity bound on gradient or maybe Hilbert on the gradient implies regularity, and this pathetic little bound on the gradient. Okay, so there's a gap. But I think there is physics behind it. So another way you'll see at the end, I'm going to mention some stochastic things. Majority of events will be this event. Now I'm going to talk about why actually the two problems are different. And in Navier-Stokes, there is a famous condition. So why they are different? Navier-Stokes is a blow-up for the momentum. It's a blow-up of the velocity. Velocity has to go infinite. Euler is a blow-up of gradient. So that's the difference. So you'll see here, in Navier-Stokes, there are famous old conditions. I give only one of them due to Prodi, Seri, Ladygensky, Voyage. People mention lots of names. Prodi and Seri. So let's say that if the maximum velocity is square this time integral, then everything is fine. And this is for Navier-Stokes. And what's known, which I call FGT, Voyage, Diopeteman, and Tartar, I mentioned the second, what's known is that the time integral of u in infinity is bounded. This is a very nice bound, actually. It tells you that, bounded by the energy bucket, by whatever energy you have initially. So this tells you that you cannot carry any blow-up that occurs. If you think it happens here, it will happen at most at a distance, this is a distance. At a distance that's prescribed a priori, you cannot go back. So you cannot miss catching it. But there is a gap. Okay. There is no such thing for it. So there is another class. So these are all classical functions. L infinity is bounded. L3 means the third power absolute value is integral. So there is another very important, and in this talk will become more and more important if the talk can go on a little longer. L3 bound. So there is the Voyage, the Prodi-Seri conditions go for other LPs at infinity, but they stop at L3 for a reason, and that is that this is actually a Bashar theorem, and was proved essentially by contradiction not very long ago by Escariaza, Seregin, and Schwerer, and that says that if the maximum of the L3 norm is bounded, then things are okay. And for L3, what's known easily by some interpolation and stuff is that the L3 norm is not bounded, but rather integral to the fourth power. So there are always these tantalizing differences. It's not like the thing is completely hopeless. There is a finite distance, you think, especially if you're not an expert. There's no such thing for Euler, no such thing for very good reason. Euler is not really controlled by velocity. So the Navier-Stokes problem is really very different because of that. You need to create infinite momentum in the problem, infinite velocity, then you might think at first, well, the Lamborghini went to maybe 250 kilometers an hour, and then things started to settle down after that. So where is that infinite velocity coming from when everything settles down? So yeah, we agree. So that's a physically hard to imagine. On the other hand, there are other experimental data in which you can very easily see that infinite velocity, and you'll do that every morning in your when you turn on the faucet and the drop falls out. Actually, the pinch off ends up by having infinite velocity for a very short time. So turn on the faucet and the drop falls out. Actually, the pinch off.
Excuse me, what the fuck?
And experimental data in which you can very easily see that infinite velocity, and you do that every morning in your when you turn on the faucet and the drop falls out. Actually, the pinch off ends up by having infinite velocity for a very short time. So Berger's equation, which is an equation that doesn't have the incompressibility and doesn't have the pressure, does not blow up if it has a viscosity, and does blow up if it hasn't. So here is the Berger's equation in 3 dimensions, and here it is. There is no pressure, there is no divergence free. If you erase this Laplacian, you shock. You create discontinuous velocities, infinite gradients. If you restore the Laplacian, the solution is smooth, and that is because there is a maximum principle. It doesn't increase the velocity.
Mm-hmm.
So for Navier-Stokes, the straightforward maximum principle that I was just mentioning is obstructed by the pressure. I struggle to find the right words. I'm not saying that there is no maximum principle in Navier-Stokes. It's simply we don't know how to find it. Maybe we don't know the right quantity. But there is, the Lamborghini fast. We would like to say things go down. But we don't know how to find it. And the usual one, which says the maximum velocity goes down, well, you try it and you see the pressure. And the pressure is a non-local object. So the pressure, you'll see formulas for the pressure. The pressure doesn't depend on the point where you're sitting, and because of that, there's a problem. So there are sufficient conditions based on the pressure, Navier-Stokes. And I'm going to quote one very easy to prove. Maybe I'm going to show where it comes from. By Berseri and Galdi in O2, that says if you take the time integral of the L3 norm of the pressure, again, this test is free, you take the square, and if you knew that that's integral in time, then u is smooth. And Serogin and Schwerer, they showed that actually you need only lower bounds. You don't need the absolute value of p. And that's a very interesting and harder theorem. This upper bound things are very easy. So here's why they come. You can write down an equation for L2 evolution of the velocity. They come from the Prodi-Seri conditions. You have the conditions of integrals of velocity to some power. You take the time derivative of that. Everybody else is either dead or benign, and only the pressure survives. You integrate by the gradient of the pressure, find the gradients on velocity on the gradients that they are given by the viscosity, end up with this inequality. Q is the power that you raise u to, and if you argue than 2, you recover very nicely that if Q is equal to 2, you don't have any growth. and you take a 1 over mu.
I don't get that.
So obviously, if you put q equals 3, you would integrate this, get the finite quantity, you get everything to be bounded. Then you apply the Iscaria's Seriovian result. That's basically how this, we put around the same time, goes.
Because it's so loud, this scares me
So
so much.
now, for those who are patient and are still with me, I'm going to write down some formula for this. Now, the gradual ramp moves up a few notches, and the degree of boredom will increase dramatically, but I'm going to write formula. Okay? So those who are interested in these will use it. I believe that they're very interesting and very important. So we start with taking, this is the equation that the pressure satisfies both Euler and Navier-Stokes. It is the statement that the divergence of the momentum equation is 0. In Navier-Stokes, that momentum equation had a Laplacian of a function with divergence 0, and there were no boundary conditions. So when you take the divergence of the Laplacian, it goes inside the Laplacian, it vanishes. So this is the equation. And we don't have good boundary conditions for the pressure, except in trivial cases, it's periodic or at infinity might be in case. So these are the equations, and we're going to try to express P in terms of U, locally. Okay, so that's the news, this is a on local thing, you can invert this and get 1 over 4 pi integral x minus y right hand side y. Okay, that's the fundamental.
Is a sphere just for
but that
simple
requires you to know the
mathematics?
velocity.
The cube?
So U is given divergence 3 at this point, doesn't need to be a solution, but of course we are thinking about solutions. And we're going to take spherical averages. This is this will be on your test, okay? This is on your test in maybe second year, okay? So you take spherical averages. It's essentially level of Fritz John's book on the take spherical averages of denoted by bar at distance r. So this is the ball of radius r around my point x, and I take a spherical average. The only little trick I'm going to do, which is pure luck, I think, is that I'm not going to talk about the pressure. I'm going to take the pressure, or the pressure average, and add a thing to it. And it turns out, by luck, that this thing is what is needed. And this is actually what it is. It is the average at the same distance r of the velocity dotted into the direction. So if I'm here, I'm
A sphere, we define the sphere. Okay.
taking r direction, I have radius, the velocity is a vector. I project that velocity on that radial direction. It's called the longitudinal component of the velocity, and that is squared and averaged on the sphere. So I call that B for bounded. This object will be bounded. So there is, once you do this, there is a monotonicity lemma. Those of you who know elliptic equations, monotonicity lemmas are an important thing. And in this particular case, I put quotation that maybe not monotonic, but you have a local ODEs, if you wish. And this is on the web now on my webpage. So you take a point, you take a place, and you take any solution, including the harmonic pieces that are there. I take any vector, and I compute the r derivative of this average pressure plus something, and I get an equation. An equation has a nice symbol. This is simply the unit vector monomial. This is the Kronecker delta, and this is the displacement between u and an arbitrary vector b.
It's like sort of makes sense, but also like,
tells you that r
what the
derivative
fuck
of
am
the
I
average
watching?
pressure
You
is
know,
proportional
like
to velocity increment integrated against harmless things. Okay. So here is hard representation for.
the cameraman should be shot with a gun. Like, come on, this 2013 Princeton camera is really that bad.
With this representation formula, number one tells you that p minus v bar is averages of squares of increment. And all the knowledge is in a ball of radius r and r is arbitrary. And I don't need to know anything else. So, in order to digest this for a second, think in terms of orders of magnitude. So it tells you that p minus v bar is of the order delta r u squared, where delta r, let's say, is the supremum, and distance r, I take the modulus of the distance between the vector u at distance r and the vector u where I'm interested, square that, call that delta r of u, and I have here that p minus v bar is of the order delta r of u, and this is an average, the r rho over rho of the same thing. So the fact that p is arbitrary is exactly here, because p is known up to an harmonic function. But for an harmonic function, p minus v bar is here. So this is determined by information of the pressure totally, the information about the velocity totally and locally, modulo p. Now, I said that p bar is bounded, I like, but it will be bounded in a second. So I take a wave function that looks like a ramp, 1 up to 1, and then goes down to 0, and then continues to 0. This is a
Yeah, that's basic ramp function.
wave
From
function.
the control
Then I
theory.
represent the pressure as now something really bounded, delta, and the rest, which is an oscillation. And delta is again one more average of p bar. P bar was a spherical average. Now this becomes an annular average. It's an average of the annulus of the pressure. And now this is going to be, you'll see in a second, is going to be bounded. So pi is simply the average of that thing before. You don't need to remember anything, of course, but essentially here's the annulus. You have the annulus, you have increment of the velocity with respect to the center. So that's what you need to remember. You have a singular integral with a very nice symbol, and very classical singular integral. So we have some bounds. Okay, so let's see. When am I supposed to end?
Omega is at 13.
Okay. So let's go a little fast to the bound. And I promise this is bounded in two ways. If I have only energy information, remember that's conserved both Euler and Navier-Stokes, or bounded with Euler and Navier-Stokes, I pay a price of r minus 3. If I have H1 information, which is also integral in time in Navier-Stokes, I pay r minus 1. And this comes easily. And now, if I take the representation that assumes decay at infinity, only now I'm doing that, which means that the pressure is an expression in terms of Ries transforms and U, then I get uniform bounds just from pressure bounds, uniform bounds that are known essentially.
I don't know why I was thinking about this right now. Like, I don't know. I sometimes watch some people, such as like Ludwig, etc. Is that how he feels when he's presented with like a basic math problem? I've seen in trivias and when watching YouTube, people get asked like whatever questions, like I don't know, what is the sum of all the numbers from 1 to 10 or something? And he always goes like, that is how I'm feeling looking at this. I'm not claiming that I'm better. I just fucking. I am struggling with this shit.
For the pressure that do not depend on that. And then I can interpolate between this and the infinity, and I get any kind of decay at the price that interpolates between these. Okay, and then also I can get for the gradients a bound that is in terms of L3 and gradient 2. Remember, I care about L3 more than other spaces, so this will give me a bound for gradients. How about the other guy? The other guy is small. So the other guy is small if the velocity is really continuous in a very simple way. So this increment needs to vanish with z at any decent rate. Any decent rate. So I'm having a singular integral here. And this is the first bound. The consequent are that pi is like r squared times the gradient. Okay? And in particular for L3, which I like, this goes like r squared times Laplacian. But the Laplacian actually, we have also these bounds that are known for all the pressures that are independent of that. So for the dynamic space tells me that the Laplacian is integrable in weak solutions of Navier-Stokes to small power. So that means that pi in L3 is less than a constant times r squared. And that constant is almost everywhere finite in time, but only because 1/3 power of that is integrable in time. So there are singular times, and because of that, I cannot say that this is less than 1. But if I knew something, so these are not criteria for non-GOA for in terms of pi. So the main idea is the following: beta or base bounds which guarantee global regularity at any time. So if I could ignore pi, I'd be done. And the other thing is pi is small for small r. So number of units passed, and we're done. However, we have to actually do the job. So here is one possibility. Imagine that not only that I take r, I'll take it as a function of time. Let's pretend that the thing blows up at capital T, and I'll take it as a function of time that goes to 0 at capital T, but it will have to go to 0 not too fast. And then when I look inside pi, I require only to look at regions where the velocity is larger than some huge velocity, like the Lamborghini. And so I look there and I discover this L3 square is fine. Then U is fine. U and all the constants are fine. Or if there exists a U like before and the same kind of r, and I have a bound pointwise at r of t that diminishes in time, a bound in terms of beta, so actually I'm saying pi is less than beta, or maybe pi is less than beta plus u squared, or maybe pi is less than beta u squared, another function that's in L2 of L3. Okay, whenever u is large, then u is infinite. So in particular, if the steady condition in L6 is valid on the region where velocity is large, you have LED. So those are essentially translating into elementary really consequences of the formula, and the common sense that in principle pi should not be there. All right, so I would like to, I have a couple more slides about outlook if you don't mind. So I'm going to skip this. Okay, so this is these are the discussions. I'm not. So there are other models. So there is absence of anomalous dissipation in a model called SQG, and that's where it's equal. There is presence of anomalous dissipation in some dyadic models. That's the work by Chesil and collaborators. So there are models in which you can construct this non-vanishing flux. There are other models also. Breakdown for smoothness for large data in waterways is the recent work of a Spanish. I'll make Charlie honorary Spanish, so then it's a Spanish group, and the Scotland and Shore. There is global regularity for small data in waterways, which is a very complicated problem, and these are recent results. It's harder. I'm going to quote two large data solutions that are really very special. One is all by Professor and Reddick, which is really very non-trivial, and an amazing result for Philly is a model for complex fluids by another Masudi. We wish we had this week's solutions in more equations for complex fluids, but we don't know at this point. And large data results of the kind that we would like here for dissipative, critical dissipative SQG, the results by Nazarov and Goldberg, and we have much more later. The result with Vladiko that I think gives the proof from the book.
A lot of Italians and Russians.
There are results that take advantage of special structure for the pressure and prove total regularity for.
Is it Chow TT or Sao TT or Kao TT?
There's a result, it's an easy result, we can imagine legal, and already it's another complex model that is open, kind of like surface fluids. And very recently, two amazing results about on-time behavior, one by the Rossi and Masudi, kind of like quote-unquote lambda damping, so people heard about lambda damping, but this is stability of Couette linear shear, Riemann linear, and a very recent, our workshop result about super exponential growth of gradients in 2D Euler by Islet and Scher. So these are amazing results. And then there's medical evidence in our workshop by Tom Howell.
Axisymmetric 3D early blow up, how low?
Axisymmetric 3D Euler blow up due to boundary difference. Something that we didn't talk at all today. So here, this is my last slide. I have 3 bullets here.
Okay,
Boundary effects,
effects,
it's not only because of the recent work of
ability,
Tom Howell and Lowe.
irregularities,
For diffuse bound, it's generated at the boundary. All turbulence is generated at the boundary. I didn't talk about the zero viscosity, the presence of boundary. That's an essential open problem, and that is not understood. This is a little hobby horse of mine, stability implies regularity. If you formulate it in some sense, L2 stability of fluid solutions shows regularities. In other words, the things that you observe are the things that are observable. It's a tautology. But it has a little bit of beef, not a whole lot. And finally, stochastic description. So there are stochastic descriptions, meaning that you can represent the deterministic Navier-Stokes as an expected value of the stochastic process. But there are also issues with enlarging the whole description in which you allow for stochastic forces. The purpose of this would be perhaps to understand the statement of what are the chances of actually have the Lamborghini pass and the velocity going to infinity while on average goes down. So can we actually, if not prove that for all possible cases, can we actually understand that this is really what's normally happening? And that would require a little bit of stochasticity. So with that, thank you very much for your attention. And sorry.
All right. I think I'm done for today. So, how do I conclude part 1 of my series? What can I say? 1, I knew I would not understand shit, and I do not understand shit. It's going exactly to plan. 2, I need to research the existing theories and laws. Hours and hours. I really hope AI makes it not like easier for me because I'm missing a lot of basics. Like I have the super basic math, but the notation, existing theories, and certain trivial steps are non-fucking trivial. 2 hours spent, nothing achieved aside from scoping the issue. I've realized that I may be even more fucked than I thought I was. However, we keep going and eventually it's gonna work. Never give up. Never give up. Never give up. One day or day one.